Yes, a phase change by the power company could cause motors to rotate in reverse. The phase of the power supply dictates the rotation direction for single-phase motors. A change in phase will alter the motor's rotation. You can reverse the direction of rotation of a 120-volt motor by switching the leads. The direction of rotation is determined by the current flow. Switching the leads changes the current's direction, thus reversing the motor. As for troubleshooting the issue, firstly check the phase of the power supply using a phase tester. If the phase has changed, correction is necessary. Secondly, inspect the motor leads. Ensure they are correctly connected. Loose or damaged leads can cause reverse rotation. Thirdly, check the motor brushes. Worn or damaged brushes can also contribute to reverse rotation. Finally, if all checks fail and the motor continues to rotate in reverse, motor replacement might be required. Let's delve into more detail. Single-phase induction motors, unlike three-phase motors, do not inherently have a direction of rotation determined by the phase sequence of the supply voltage. Instead, the direction is determined by auxiliary methods employed to create a starting torque. Several types of single-phase motors exist, each with its own starting mechanism. Split-phase motors utilize a starting winding in addition to the main running winding. This starting winding is typically connected in parallel with the main winding, but it has a higher resistance or inductance to create a phase shift between the currents in the two windings. This phase shift generates a rotating magnetic field sufficient to start the motor in a specific direction. If the connections to either the starting winding or the running winding are reversed, the direction of the rotating magnetic field reverses, and the motor will run in the opposite direction. Capacitor start motors are similar to split-phase motors, but they use a capacitor in series with the starting winding to create a larger phase shift. This results in a higher starting torque. Again, reversing the connections to either winding or the capacitor will reverse the direction of rotation. Capacitor-run motors use a capacitor in series with one of the windings, but the capacitor remains in the circuit during normal operation. This improves the motor's efficiency and power factor. The same principle applies reversing connections reverses rotation. Shaded pole motors are a simpler type of single-phase motor that use a shading coil around a portion of each pole to create a small phase shift in the magnetic field. These motors have low starting torque and are typically used for low-power applications. Reversing the direction of rotation is not typically possible with shaded pole motors, as their construction inherently dictates the direction. Universal motors are series-wound motors that can operate on either alternating current or direct current. The direction of rotation is determined by the polarity of the voltage applied to the armature and field windings. If both the armature and field connections are reversed, the motor will continue to run in the same direction. To reverse the direction of rotation, only one of the connections needs to be reversed. Now, considering the scenario of 350 motors rotating in reverse simultaneously, the probability of all motors having individual wiring faults is exceptionally low. A more plausible explanation involves a change in the incoming power supply. While the power company cannot directly change the phase of a single-phase supply in the same way as they can with a three-phase supply, there are scenarios that can mimic this effect. Firstly, consider the possibility of a wiring error during maintenance or upgrades on the distribution transformer that serves the facility. If the connections to the transformer windings are inadvertently altered, it could result in a reversal of polarity on the 120-volt output. This would effectively reverse the direction of the rotating magnetic field in the motors, causing them to run in reverse. Secondly, investigate the neutral connection. A floating or high-resistance neutral connection can cause voltage imbalances and erratic behavior in single-phase circuits. This can manifest as motors running erratically or even in reverse. This is particularly likely if the motors are connected to different phases of a three-phase distribution panel. Thirdly, consider the possibility of induced currents from nearby equipment. Large inductive loads, such as welding machines or other heavy machinery, can induce currents in nearby wiring. These induced currents could potentially interfere with the operation of the motors, causing them to run in reverse. To diagnose the problem systematically, firstly, use a voltmeter to measure the voltage at the motor terminals. Ensure that the voltage is within the acceptable range and that there are no significant voltage drops. Secondly, use a phase rotation tester to verify the phase sequence of the incoming power supply. While a phase rotation tester is typically used for three-phase systems, it can also be used to identify polarity reversals in single-phase systems. Thirdly, use an oscilloscope to examine the waveform of the voltage and currents at the motor terminals. This can help identify any distortions or anomalies that may be causing the problem. Fourthly, check the grounding system. Ensure that the grounding system is properly installed and that there are no loose connections or corrosion. A poor grounding system can cause voltage fluctuations and erratic behavior in electrical equipment. Fifthly, inspect the wiring connections at the motors. Ensure that the connections are tight and that there is no corrosion or damage to the wiring. Sixthly, consider the possibility of harmonic distortion. Harmonic distortion can cause a variety of problems in electrical systems, including overheating of equipment, reduced efficiency, and erratic behavior. If harmonic distortion is suspected, a harmonic analyzer can be used to measure the levels of harmonic distortion in the system. Seventhly, consult with a qualified electrician or electrical engineer. Diagnosing and repairing electrical problems can be complex, and it is important to have the expertise of a qualified professional. To address the specific suggestions provided, firstly, checking the phase of the power supply using a phase tester is not directly applicable to a single-phase system. However, as mentioned earlier, a polarity test can be performed to ensure that the wiring is correct. Secondly, inspecting the motor leads is crucial. Look for loose connections, damaged insulation, or incorrect wiring. Ensure that the connections match the wiring diagram for the motor. Thirdly, checking the motor brushes is relevant only to motors that have brushes, such as universal motors. If the brushes are worn or damaged, they should be replaced. Fourthly, replacing the motor should be considered as a last resort after all other possible causes have been ruled out. Before replacing the motor, it is important to verify that the replacement motor is compatible with the existing electrical system. Additional points to consider are the type of motor being used. The effect of lead switching depends on the motor type. For example, a capacitor start induction run motor has a start winding and a run winding. Reversing the leads on either winding will reverse the direction of rotation. A permanent split capacitor motor has only one winding, and reversing the leads will not change the direction of rotation. If the motors are all the same type, then the issue is likely related to the power supply or wiring. If the motors are different types, then the issue may be related to the individual motor wiring. Furthermore, the age of the motors should be taken into account. Older motors may have deteriorated insulation or worn bearings, which can contribute to erratic operation. It's also worthwhile to investigate if any recent electrical work has been performed in the facility. A mistake during electrical work could easily lead to a wiring error that causes the motors to run in reverse. Consider external factors such as changes in load or environmental conditions. A sudden increase in load or a change in temperature can sometimes affect motor performance. It is also necessary to ensure that the motors are properly lubricated. Lack of lubrication can cause the motor to overheat and run erratically. Check the motor nameplate for the manufacturer's recommended lubrication schedule. Also, check the motor's overload protection. Ensure that the overload protection is properly sized and functioning correctly. Overload protection is designed to protect the motor from overheating due to excessive current draw. If the overload protection is not functioning correctly, it could allow the motor to run in reverse or overheat. Finally, documentation is critical. Maintaining accurate records of all electrical equipment, including wiring diagrams, motor specifications, and maintenance logs, can greatly assist in troubleshooting problems. Thorough documentation allows for a faster and more efficient identification and resolution of issues. In summary, the most likely cause of 350 motors running in reverse simultaneously is a problem with the incoming power supply or a wiring error. The steps to take are to systematically check the power supply, wiring, and motor components. If the problem cannot be identified, it is important to consult with a qualified electrician or electrical engineer.